Over the last couple of episodes, I used this mental model that's using just a table with the type, name, and value, and all operations refer to variables that are stored on this table. Int A could be a 3, maybe a bool. B would be false. Float F would be 1.234, for example. And for just learning ropes to get your feet wet, this is perfectly fine. This is a pretty good model, I think. I still use it, I like it. But it is, of course, hiding the truth a bit. And today we're gonna kind of peel back a bit on this, scratch the surface up a bit and see what's underneath. Because the simplification I made with this model is the computer doesn't actually operate on this system with a table that's neatly arranged and just ready to be used. If you remember the very first episodes on the fundamentals of what's happening inside your computer, what we actually have is just a long sequence of individual memory cells, which we can access through different commands, through operations, where we can change values in individual cells, where we can read individual cells. And we've also looked at how we can combine multiple cells to make larger values. Well, we sort of looked at that, I mentioned it at least. And that is of course happening with C# as well. Not all the types here fit neatly into a single memory cell. Usually today's memory cells are a bit larger than our 8-bit cell system initially in the very first episodes, but still sometimes we need to squish a couple of cells together. In the end though, it is still memory cells in a long list of memory cells. Not some convenient table. This is just to visualize it for us squishy human brainies. Instead of a table, what the compiler would use, actually let me write some program code that matches this. And we had the bool B, which was false, and the float F, which was 1.234. Separate that a bit. So when I go, all right. If B, then A equals A plus 2, like that, and F times equals 3.14, whatever. When we read this code and apply our model, we actually go through this table and check. We assign 3 to the variable named A to that row, and B applies to the second row, and F to the third row. So when I check if B, I'm actually looking up the second row with the B and check that value. And when I manipulate A, well, for reading A in here, I go to this first row, and then for assigning a value, I also go to this first row. And then down here, for this multiplication with F, well, I check F, multiply it with our constant value here, and then write that back into this third row. The computer doesn't see this table, so it's not like it's trying to find a row that has a specific name in it and uses the values in that row. When we compile this program, what would be still not the actual way it happens, but a bit closer to the truth, these names are kind of replaced by the actual row we need to look into. So instead of if B, we might check row 1. I'm just going to use the pound symbol or hashtag, depending on how you're used to it. And down here, oh wait, that's not 1, that's 2. And this would be 1 equals 1. And for F here we would use 3. So the names are relevant for the source code, but once it's compiled, these names are gone. Like the compiler doesn't even know those names anymore. They're only relevant while we check the code and try to understand it, but once that's done, all the computer cares about what's the value and how do I interpret this value. Because in the end, the value is just a sequence of ones and zeros. The computer needs to have some understanding of how do I use those values. So the type still needs to be included in some way. But we're not actually working with names anymore. The compiler has sorted that out, and instead we're working with addresses. The memory addresses. If you remember then from the beginning, we never had variables, at least in the pure assembly. Well, no, in the assembly we did have variables of sort of, but in the machine code, we never worked with variables in some neat fashion. We always had to work with specific memory addresses. And we abstracted that away with memory references, where we could just use a name to refer to a specific memory address. And this is that concept, just a bit more extreme. We have a variable called A, which in our mental model meant we have an entry in this table that includes the A, but to the computer it just means we have a memory address. We don't exactly know where a memory that address will be, but we know there's a memory address. We just use the shorthand A for now, and down here I refer to this address with an A, and I replace that now with the address we're actually going to use. Use that in here as well. And because we're working with addresses and not actual variables that are locked into the specific table, there are things we can do. See, these addresses are in the end just numbers, right? They're integer number that refers to a specific position inside your memory. They're just values you could store. And if you think about machine code and assembly, what we did a lot is use specific memory cells, the content in specific memory cells, as the address for an operation. And these addresses could be altered. We can read them, we can manipulate them and change them. We can use them for calculations. An address is, in a way, just a different kind of data type. This 3 is just an integer value, a mathematical value, a number that can be used in different kinds of ways. We can compare it with other things, but we can also apply mathematical operations on it. This is just a true or false. It's a Boolean value that lets you do some simple logic decisions. And similar to that, addresses are also just a different data type. In that case, we would look at the number, for example, a 3, but don't treat this as this is just a number 3. No, this is referring to an address in memory. It is the memory address 3. We refer to a specific memory cell. Kind of. And C# allows us to actively work with these addresses. In general, I could be referring now to pointers, which would be a more formal name for this concept. A memory address can be stored inside a variable, and this variable, a specific type of variable that contains an address, not just any value, but specifically an address to the memory it is held in, it's called a pointer because it points to a specific point in memory. C# does have this concept of pointers, and there are specific types to deal with pointers, and there's a specific syntax around it, but we're not going to use it. C# lets you do that, and there are some cool things you can do with it, but generally you should avoid using pointers if possible. Especially in older versions of C#, you sometimes had to use them for performance reasons, which is why in newer versions of C# they added different object types, a term we will learn about later, and different libraries that gets you almost the same performance gains you used to have when using pointers, but without using pointers. And there are some built-in ways that were, well, I'm not sure if they were always in there, but they're a very old feature in C# that lets you interact with these addresses in a way without using pointers, of which we will look at one example first, just to ease us into the entire concept of working with addresses and not any values anymore. That works out. Let's make a simple program. Let's make this. No, actually, let's make this differently. Oh yeah. Let's be very simple-minded here. Int a equals 1, int b equals 2, and int c equals a plus b. All right, let's keep it simple. That's our simple program for now. Straightforward. We create an a, we create a b. One receives the value of 1, the other the value of 2. And then here we calculate the sum of both of them and store them in a new variable c. All right. Then let's say we have a method that replaces this operation. And for starters, this could be straightforward, add int a, int b. And this will return a plus b. Simple, straightforward. So we now could call the add method instead and provide a and b. Replace the direct addition with a method. Which, okay, for addition, not really worth it, but just to demonstrate the code, this is also pretty simple so far. At least if you've paid attention in the last 2 episodes. Well, the 2 episodes ago? 2 episodes ago. This is a method call. We provide a value and a second value for the 2 parameters. They're both declared in here. And when we call this method, we go to a new stack frame. We are first in this code, which is 1 stack frame, which in our model was type name value 3 rows. We had int. This was A, B, C, and this is 1, 2, and this is where we are currently operating. Actually, at this point, the int C doesn't exist yet. We make the method call for A, B, which turns into a method call with 1 and 2. Resolve the 2 variables, the 2 references to a member in this table. And this method call will mean we enter a new stack frame. We have a new table. This is entirely separate from this old table. This is not a new scope. This is not a second table directly below the other table. We don't have access to this table anymore. This is a new stack frame independent from this old stack frame. But because this is a method call, we can start, before our code even starts, with two variables, int also called a and b, no relation to this a and b. And because it's a method call, these two variables, which are parameters, are pre-filled before we even start our code with the values we provide up here. So that. So this is our second table in the second stack frame. Now we can perform the addition with a and b, which is 3, and then we return the value, which is essentially the result of this method call. The operation which is a method call. And so we can then create a new int c, set it to 3. Of course, once we return, this table is removed. We go back to this stack frame up there. And last time I demonstrated to you a way we can provide a value for the variable c up here without returning it down here. Can turn this into a void method, and instead of returning a and b summed up, we can simply say that at, and actually let's shorten this a bit, save a bit space, int a, int b. We can define an out parameter with the out keyword, and then int, let's call it O. Could be C as well for consistency, but actually I want to avoid confusion later on, so I'm just calling it O right now. Also, that's not good. Let's call it just D. And so we have the option in here. This is now a void method, so we can provide a value with it directly. We can't put it in as assign it to a variable. This doesn't work. Add doesn't provide a value, but we don't need to anymore, because in here we can also essentially verify that yes, we know this add method will provide a value through an out variable. We confirm that by defining this as out as well in here, and then we can write int c in here, have the method, the variable declaration inside the method call. And now we can set d to a plus b. And when we now call this method, we do still enter new stack frame. But we do so after, in this case, for declaring a variable c. It doesn't have a value yet. But inside this method call, we sort out a and b, which is then just gonna be add. Actually, let's go through this in steps. Why not? So we start with, let's make this bigger. So we start with add a, b, out int c. And then we can resolve this to add 1 to 2. Those are just lookups. I'm just gonna put them all on one go. And for this one, well, we declare a variable c. So now we have just out c. And this is now a valid method call. Out c remains as it is, because we are essentially just rerouting a data flow into variable c. Similar to how we can say c equals something, like c equals 3. We can use out c in this case to redirect a value into the variable C. So far nothing happened, so it's still undefined. But once we open the new stack frame and start this new method, we still have the new table. And I'm noticing I'm just reiterating the out variable, which is maybe not the worst idea. Int A was pre-initialized with 1, and int B, which was initialized with not a 3, with a 2. And lastly, int D, which didn't receive a value. So it's only declared, but it's not initialized. It's undefined so far. And now we can start operating on this, where we have the operation d equals a plus b. We'll resolve a and b, so this is 1 plus 2. So d equals 3, and now we can assign that. Set d to 3, now it is defined. It is still a parameter, just like the others. It is declared before the method actually starts. It's just that because it's an out variable, it's never defined before we start, unlike these two normal parameters up here, which have to have a value before we can start our code. And now the method has ended. It's a void method, so we don't need to provide a return value. The return happens automatically, though I can, of course, add a return manually. I just don't provide a value. But since I don't have to provide a value, I can just end the method and it will work just fine. We've done all of this. And now we go back up here, we leave the stack frame, but something special happens. The value we inserted in here, because it's an out variable, is copied over to up here. So while our method, if it was just the int add from before, would be effectively replaced by a result value, this is just a void method right now, so it doesn't result in any value. The out variables are still copied back, just like the 1 and the 2 from up here were copied downwards when we started this method. When we end this method, we copy the values from the out variables, in this case int d, into the respective positions in the caller. So when we go in here, we initialize these parameters and copy the data that was provided up here into this table, and then we execute our code. And then when we leave the method, we go to all the out variables and copy the data back to the caller, to the parameter, so to speak, that were provided in the call. And then the entire thing, if it has a return value, is replaced by the return value. Meaning that in this case, 3 is assigned to C. That's the out variable. And that wasn't entirely clear earlier. I can just declare an int C like that and directly use it like out C. I don't have to declare a variable in here. It's just that happens quite commonly. Because why waste a second line on that? If it's the first time you use the variable, just declare it inside here. It's just shorter. Saves a bit of space and a few less characters. But you can declare it beforehand and assign it here. You can also initialize it. You can actually provide a value for C, that's fine. You only have to provide a variable in here. It's just you are allowed to declare a variable, to create a new variable. You don't have to use it, you can though. So the out int C was actually a special case. Usually you just provide a parameter, just like the other ones, and you mark it with an out. So the caller confirms that this is an out variable. It will receive a value when the method goes back, and these are input parameters. They will provide a value when the method gets called. All right, so far so good. Now let's go back to what I mentioned earlier about variables not actually being what's used inside the computer. When we compile this code, all these references, all these variables are effectively replaced by a memory address. So going from add A, B, out C, we go to add memory address 1, address 2, address C. Which still does the exact same thing, it just internally happens a bit differently. But we can take advantage of things a bit. What if instead of telling the compiler that we want whatever value is returned to be put inside memory address 3, the memory address for C, we give this other method our memory address and we let it fill that memory cell directly. Right now we're getting back a value, the number 3, and we put that into memory address C. That's what happened earlier. We copied the entire value directly in here. But we can provide this add method just the memory address directly as a normal parameter, sort of normal parameter. And if we do that, this method is not isolated anymore. Before, this was a new stack frame with its own table. It has no idea how this table works. It has no relation to it, no access to it. It doesn't exist as far as this method is concerned. But once we provide the memory address, the actual address inside memory, then this method suddenly has a way of interfering with this table above, or at least one specific position in here. And we can do that by simply changing out this keyword out. Yeah, changing out. No pun intended. We change it to ref for reference. What this is doing is we tell this method you can provide the value for A for the first parameter and the value for B for the second parameter, just like before. But once we get to this third parameter, don't provide the value in C, which at that point would be 0 because we initialized it with 0 up here. Don't provide the value for C. Ref C means provide the address for C, this memory address. And down here, it is equally marked with a ref to make sure this method knows, hey, you don't receive an integer value directly. You receive the memory address, a reference to an integer value. Which has an interesting effect as far as the rest of the program is concerned here. We're using int d just like we use int a and int b. It's just a variable, it's just a parameter. We can use just the integer d. Nothing special about that. When we call the method, we still declare the variables and we still pre-fill them with their data. So for A that was provided as a 1, for B that was a 2. But now for D things get interesting because D is now a reference to another table in another stack frame. We don't actually have a value in here. It's not even in the table. And as we have a fake entry in this table, we can use the variable d. But again, the compiler doesn't use this table with all of these names. The compiler effectively just uses memory addresses. And for A and B, those memory addresses are in this new stack frame, in this table. So when we reference A and B, this would be, I don't know. Okay, now the naming from earlier is a bit confusing. This would be, let's use this 4 plus the address for 5. Let's just say this is 4 and this is 5. Right, so it refers to these two memory addresses, which happen to be in this new stack frame that exists for this method. But when we assign it to D, it is not using a new variable D that we added in this table here for this new stack frame. It is not a new variable. We use the address that was provided from the caller, and the caller had this in memory address 3. So when we add these two numbers, we reference from address 4 and 5, A and B here. We assign the value 3, the number, to memory address 3, which is not part of our stack frame. It is part of this stack frame up here, for this method. It doesn't matter though. As far as the computer is concerned, we are always just moving data between different memory addresses. This whole separating this into stack frames, well, the computer does have to do some work with it. There is some use for that, but technically, this is just one continuous memory. There is not really a separation in memory between these stack frames. It's just, we have some rules that prevent us from just going back and forth all the time. Which is why our mental model separated them into different tables. But it is technically one continuous memory, which is also why I continued with memory address 3, 4, 5. Because it is one continuous piece of memory, sort of. So what we did now, we wrote the value inside this memory cell into this table up here directly. So even before this method returns, we've already changed values in this stack frame, because we're editing this memory address. We're not changing a value inside a table with our model, we're changing data in memory. We're closer now to what the computer actually is doing. And so the method can return. We go back up here. We don't provide a return value, so nothing else really happens. And unlike with the out variable, where we actually would have to copy data over now, we don't need to do anything anymore. This was just one-way street. This is going down, this is going down, and this is strictly going down. With the out, we actually go back up in terms of data flow. But this is a ref. We only send data one way when we call the method, and it's only the memory address, which is then used as if it was part of this stack frame. It is like a ghost entry. It does have a name, we can refer to it. We can create a custom name for this, but it's not really part of the memory in here. It used to be 0 and then we changed it to 3, but it is actually this memory cell up here, which is part of the normal quote-unquote table for this first stack frame. I hope that concept is pretty clear, because these references, this we're moving around the address and not just the value of a specific address. We don't store just the values and then pass on the values to another method and use those values and return new values back. We have ways to move the address itself, not the data contained in there. And that means any method can edit technically any part of memory, no matter which stack frame it's from. And the simplest way we can do that is with ref. And I say simplest because it is a pretty straightforward way to do that without getting into pointer territory. So just if you ever encounter something like this, or maybe and A, stuff like this, multiplication sign, the asterisk, behind a data type, this is a type of pointer. This indicates that this is now pointer type, and this AND is used for references, similar to how this is ref. So ever see code with this constellation, data type and an asterisk, or a variable behind an AND, those are operations that have to do with manipulating memory addresses directly. Okay, you wouldn't actually assign 5 to that int pointer, but details. We are not gonna touch pointers. That's unmanaged code. Because if you can understand that we're manipulating data in this other stack frame, now imagine there are no rules to how you can manipulate this table. Right now, the compiler, if you use this ref keyword, has understanding of the situation. We know we want to manipulate a memory address from up here, from down here. And we do so in a way the compiler understands, so it can check what we do. It knows we have an integer c up here and we have an integer d down here, so whatever operations I do perform on d will be valid for c as well. Those are both integers, they work the same way, it's a legitimate address. Okay, I can work with that. If you work with the addresses directly, well, you could suddenly write a completely different value in here or interpret this in a different way that the compiler doesn't anticipate. Or you can do some fun stuff like overflows and underflows where you manipulate one address but change other addresses as well. And so the compiler doesn't check that anymore. Oop. Something just... Was that my imagination, or was that the Windows sound for something disconnected? Some USB device, maybe. I'm still... No, it's still... Alright, let's not touch that cable anymore. So managed and unmanaged code would refer to this being managed because the compiler manages all our memory operations. It knows what we do and it keeps an eye on things, and we're not allowed to do anything it doesn't like. Well, that might be dangerous. Unmanaged code would be, yeah, you just tinker around in memory as you wish. The compiler doesn't check anything, it doesn't ensure anything. You're on your own now. Which can be beneficial in some cases. As I mentioned earlier, it used to be one of the ways you get performance. But it's also a lot harder to make safe code because you can very easily create very hard to detect errors. So we're not going to touch pointers. We're always using managed code, and the easiest way to get access to references is through the ref keyword. Now, armed with that knowledge, let's get a bit more complicated. Just a little bit. If you understand that concept from earlier, then this next part should be actually fairly easy. Well, let's do the program I was thinking of earlier. If I could write, please let me write. Oh, that's better. Let's say I have num a equals new num. Oh, What do we do? What do we do? Let's just use the 1. No, let's use a 10. Go a bit bigger. So 10 and a true. Now, what am I writing here? This is a struct, a custom type called num. And num has an integer. Let's call it value. And a boolean called positive, which is maybe kind of useless. Let's turn this into uint. And then we have the constructor. Public is not a thing you understand yet, should not mention that. Constructor, special method, doesn't receive a void in front because it's not a method that can return anything. But it's also a special method that can only be called once. It's a special constructor method. So it's not having a specific return value. It is already predetermined what this does. And it will receive an uint v and a bool, no, not a semicolon, comma, bool p. And I'm running out of space here. Let's make this in one line. Value equals v, semicolon, and then in the same line we're just going to do positive equals p. And let's close that out and that. Okay, so we have a struct with a simple constructor that receives a value, and we now store a unsigned integer value. So we get the full 32 bits for a positive integer number. And we use a separate boolean to determine if that number is supposed to be positive or negative. So it's basically an integer, only we have 1 bit more space. For all good that does. And now let's make another method. NumB, another method, another variable, new num. This one is gonna be 11 and also true. And now I want to have yeah, let's make a method down here. We're gonna call it add. Gonna make an add method that receives num a and a num b, and it's supposed to add these two together. And you know what, actually the details don't even matter. Let's save some space, make this a bit lower here. But we're not gonna add this as a method inside the struct, we're gonna leave this standalone. We could add this in here, but we don't want to do that right now. The standalone method receives a num a and a num b, like that, and it has some code. We're not going into that. You could simplify it if you're curious how we could do that. In simplest case, you just put these uints, these values inside a long, which is more than enough space and signed. So when you insert this value inside the long, you can use an if to determine if you negate that. So either you store long L equals value, or if it's not positive, long L equals minus value. And then you just add the two else. And then you can create a new num where you have the long, which you cast down to uint again with an explicit casting. So that would be the simplest, most straightforward method. And so we return a num in here. So we could up there say num c is at A and B. All right. I'm just going to leave this code as is right now. What is happening here in here? Well, first line is calling constructor. We're creating a new custom data type, new custom value according to a specific data type we defined, num, which internally is consistent of one 32-bit value, a uint, an unsigned integer, and a technically 1-bit value, which is interpreted as a boolean directly. So this is kind of referencing a 33-bit number, though of course in reality that doesn't quite work out, and we're using a bit more space in memory because we can't address individual bits. But sort of a 33-bit value in total. And once these 33-bit are reserved in memory, we want them to be filled according to this constructor method. We want to adjust these values, and this constructor receives two values which are just straight up copied into the value. And same down here, just with different values. And finally, we're going to call the add method, which is now getting a copy of A and a copy of B, which will internally add those two together to create a new number, and it will return that number. And now I'm noticing I'm running out of space, so I'm gonna do something a bit ugly, uglier than usual. So we go type name value again, and then separate things a bit here. Leave some space over there. So we have num A, which internally, again, this is a custom type, so effectively we have another table in here. Type name value, value would be uint. I'm just gonna call it v for value, which is 10, and bool be true. And then we have another num b, which is the same structure, again, another table basically. And then we're gonna call the add method, and we get a third num c, which is again a full table. Ideally, that would contain then 21 and true. When we call this add method and enter a new stack frame, we create a table again with A and B pre-filled, which will look identical to these two upper parts in this table. And then we create a third variable inside the code, a third num, fill that with data, and when we return, we copy that data over to here into C. We call the method, we copy this table. For B, we copy that table that would be here. We have copies of those values down here, we process them, create a new num, we copy that value up to here to C, and we're done. That would be the flow of things. That means every time we call this add method, we would copy this entire table, create a new table down here and copy that as well. We don't just copy a single simple value, we copy something larger, something potentially a lot larger. This is actually rather small still. Well, structs aren't supposed to grow too big, so it's average. But in any case, there's a lot of data in here we have to copy back and forth all the time. Now, based on what I showed you earlier, a simple thing you can do is add refs in here. We make this a ref. There's also a ref. Then, of course, we have to do that in here as well. Now, these are references we're copying down. We don't copy the table, we copy the address where this table is located to down here. So when we call this method, we're actually using the values up here. We don't need to copy the entire thing anymore, just the address, which is fairly small. It's just a single number. Special type of number, but still just a single number. It's an address after all. It's basically just an integer number with some added baggage. The only thing is when we return a value, we definitely have to copy something. Well, unless, of course, I create a new value, num_c up here. New num. Let's go 0 false. Okay, I'm writing very small here. I'm squishing things together. And then I could do this and then ref C and accept that down here as well. Ref num C. And now I have, just like earlier, another address to another value where I could directly manipulate the values in here. Instead of creating a new num inside this method and this stack frame down here that I need to copy up, I can provide already a memory address ready to be filled with the sum. And so I'm just calling this stack frame, which doesn't contain any variables of its own. It's just using the memory cells that were already used by this stack frame up here. And that's it. We're just passing on the address, so this method knows how to address these. And of course, something simpler maybe, something potentially some of you have been screaming at the screen. Put this add method inside the struct. Makes it potentially even simpler. I don't need a third parameter here. I could just create C and then call C.add, for example. And then maybe this add method would set the values in C to whatever the sum of the two provided values would be. And that way, we don't have to copy all the time all this data all this time. Which is a small thing, right? It's not so much data that the computer will actually suffer from it, but there are circumstances where these things can actually go pretty big. Not just 33-bit, but maybe 33-byte, 33,000 byte. I mean, you can potentially have very large structs. And in those cases, you don't want them to be copied all over the place constantly, because that takes a lot of time. The more data you have to copy, the longer this call of the method itself would take, because it has to first prepare the method call. It has to copy all the data down, and then even once the method is done, it has to copy data back, either the return value or maybe any out parameters. That will cost time as well. And there are things like critical path, where your application, your program you write, has to go through a specific segment of code, which cannot be avoided, and which is potentially called millions of times per second. Maybe that might be a bit too much, millions of times, but a couple of thousands of times per second at least. And maybe you have enormous structs that need to be copied over. In that case, finding a way to not copy them is going to be very beneficial to your runtime. It is, though, a type of optimization that you will not run into very often. There are use cases for that, definitely. Especially, I think, for game development, that happens a lot. But usually you can avoid that because you don't actually work with structs. So you don't have to worry about references and copying over all this data. How would that work? If you don't use structs, then what do you use? Well, let's first get rid of this ref. Let's restore this to earlier with just AB numc. And yeah, that's good enough. A struct is just a data structure. We define how a longer sequence of memory cells is aligned, how it's internally structured to handle different kinds of information along one long sequence. A is 33-bit of memory, one continuous 33-bit value. Computer doesn't care exactly what it is when it copies data around, but when we use that value, we have the instructions. The first 32 bits are to be interpreted as unsigned integer, and internally we refer to it with value. And the last bit, the bit 33, is used as a boolean. That's all the struct is. Take 33 bits and interpret the different bits inside as these different values. But as I've now shown, or at least alluded to, structs can potentially get quite big. If you have really complicated structures that require a lot of specific data and a specific organization of that data, well, these little subtables in here might grow very large, and you want to avoid that. Because memory is precious. That's another thing. It's not just copying the data from one stack frame to another that's costing time. It's also you have the data in here and then you have it in here. And maybe this method add will call another method, which then has a third stack frame, which will copy the data a third time. So you triple the amount of memory you need, and so any bit in here means 3 bits of memory are gone. That's wasteful. Another reason to avoid copying the data over. You want to refer to an existing memory cell if possible. Not always. There are good reasons why you might want to actually copy things, but it's always in the end a decision the program has to make. Trade-offs and all that. So what C# is doing is it says, all right, you have these big chunks of data, these special data types you've defined that take up a lot of space. that you don't want to drag around within your stack. You don't want to copy them all of the time, which takes a lot of time. And you don't want to have them stored on the stack everywhere, because that takes a lot of space. Then why don't I just put them somewhere else? And on the stack, you simply keep the memory address. So with our stack, which individual stack frames? Type, name, value. Like there's a table, there's a table. There's a table. Right? Individual stack frames. And that's our stack. We call a method, we add a new frame. The method returns, we drop the frame and go one back up. And every single one would store the same piece of data and copy that around. And C# now offers a way, well, I have all of this other free space in memory that is currently untapped. Why don't we make use of that? If you're using references already to avoid copying the data all over the place, you should be fine with me putting that in a completely different place. I mean, if you use the memory address, you don't care if it's in your own stack frame or the previous stack frame. You just care that it's anywhere in memory. And so maybe I put it in here, or maybe I put it down here, or here, or here, or here, just anywhere. Anywhere in memory. Doesn't need to be in the strict stack where we call methods and build on top of the others. This linear progression of method calls. No, we have this free allocated memory where we could put it anywhere we want. And everything in between is just empty. There's emptiness, occasionally filled by these pockets of data, and we just put that in here. We just remember the address of this memory cell. And just like with references, anywhere in our code, we just use that reference. So maybe they all refer to the same memory location, but all they have to remember is the address. This one has this thing, the structure, stored in this part of memory, remembers the address, and then when it calls this method, it passes on the address. Not a full copy of this, just the address, which itself it uses. I'm having Yoda issues today. Words have a specific order in which I should say them. And then this calls another method, which also just gets the address, so it can refer to this one thing in memory. Somewhere. None of them care where exactly it is, as long as they have access to that address. That's all they need. This large chunk of memory, which is just randomly assigned, well, not quite randomly, but which is basically randomly assigned different values, which we just remember by their address. This is the heap. Let's call it, I wrote stack big. Let's do this in here. And just like my sketch here, the heap is usually a lot larger than the stack, because a lot of the time, maybe even most of the time, your custom data types, your custom structures will actually be stored inside the heap. You will rarely take up space in the stack. Because you save space, it's only stored once, and you save on time because you only need to copy the reference and not the entire thing, which could balloon into very big things, which take time to process. Could be very small, could be a bit bigger, could be giant. And this code right now is already pretty close to what we need. Thing is, C# has a very simple distinction between a structure like we're used to, which stores the full value wherever we need it, and copies that over between different stack frames and all of that, and the heap, where we put the data on the heap and refer to it with a memory address. The structures themselves work exactly the same. It's still just a long string of bits inside then the heap, which we have to interpret in a specific way. That remains. The structure internally of that long piece of data is exactly the same as before. It's just we want to tell the computer that when I create a new num in here, I don't mean I want to store it on the stack. I want to store it in the heap. I want to save some space and gain some performance, potentially. The only thing I have to do differently here is, instead of calling this a struct, I'm calling this a class. I should actually rename this as well. So no, like that. And the difference now is that I don't store the table in here anymore. Whenever I say num from now on, I'm telling the computer I'm referring to this custom structure I built, this class I've defined, just like with structures. But because it's a class, the computer knows A is not the actual data anymore. A is now just an address in memory that contains a num. So this is now just another address. Which usually are a bit larger. So this is not just a simple address on the stack anymore. This is now a complex value somewhere on the heap. And because it is not structured in any way where we put the data, it doesn't have to be structured. There is a pattern to it. We'll get to it at some point. That's a bit more advanced and not really necessary for you to understand most of the time. That's optimization stuff. These values can be quite different and quite far apart and very chaotic. But yeah, these variables store not the actual numbers anymore, not the structures, but just an address to somewhere in the heap. Let's fill this out a bit more. Which actually gives a new meaning to the keyword new. I slipped up earlier. I said with a new keyword we create a new number and preserve the memory. Well, actually, no, we didn't. With a structure, at least we didn't, because the compiler knows when this is a structure, well, I need 33-bit of memory for this and for this and for this. So this table, when we create the stack frame, when this method is called, when this code is executed, we already start with the memory allocated for those three variables with 99-bit, 33 for the first, 33 for the second, and 33 for the third. That memory is already there. The stack is already pre-sized exactly to fit what we need. It is still now, after this is class, this is still pre-sized to fit exactly one memory address. It's just the memory address is a bit less. Okay. Usually the memory address is less than the structure will take. In our case, it's actually not. So yeah, it depends on the architecture, but technically no. Okay, those are nuances we will get to maybe at some point if it becomes relevant. But yeah, reserving space is not the new keyword because the heap itself is chaotic. You could put anything anywhere. No regard for any structure of the heap itself. Except, of course, I can't put something new in here. That this entire thing is already filled with other data. I have to look for some free space. And if I have something large I need to store, I need a lot of free space. So this wouldn't work, or this would also not work. I have to actually go around and look for a space that is large enough to fill whatever I need to have stored. And that takes a bit of time. So using this system with references to the heap isn't immediately faster. It can be faster than structs, like before, because you don't need to copy the data all the time, but then again, finding free space on the heap, because it's so chaotic, can take also quite a bit of time, which is why there are systems that make it less chaotic. But that means we have to actually find free space in the heap and reserve that. So we have to say, this is now our space, we want to use that. This is now occupied by our custom structure, by our class. And that's what the new keyword is actually doing here. For a structure, it's sort of meaningless because the space is already available, everything is predetermined. It's just a formality in that case. But for a class, it is actually doing something. It is actionable. It will, when you call the new keyword, when it reaches this point, it's an operation that will go to the heap and look for space that's large enough to fit a number, a num. So 33 bits. And once it finds that, it will return the address it just occupied, or at least the very first memory cell of that space it reserved. And then it will continue with the same logic as with the struct. We then proceed to the constructor, which is getting two values, which is internally assigning, just like with the structure, and we have a new num. Only now we store the address on the heap instead of the full value in here. And that also means when we now call the add method down here, what we provide down there, so let's write this out maybe. Num A, B. So these are still parameters that are pre-filled before we start executing the code, just like with integers before. And with structures, we would copy the entire value in here. And we do the same with class. We copy the entire value in here. We copy the value from the table. We don't copy the value from the heap. We don't copy the data that is referenced by this. This is just the address where the data is stored. All we copy is directly the value in this table, so the address. So this is still the address 5439001, and this is 1001199. So when this method is using A and B, it is referencing the exact same structure, the exact same spot in memory as A and B appear. I didn't need to add ref in here. There's no point. A and B are already references. You could use ref. I can't undo. But there are special meanings to that now. And it's rare that you do that. But it could do that. It is, okay, maybe let's talk about that. If I use ref in here, I would, just like before, reference these entries in the table. Instead of A and B being copies of those addresses, I would actually use this A and B directly. And when I change A and B, I could either change the data in the heap, which is what you would usually expect, but I might also change the address in here. So for example, if I were to assign a new num, as much times as this max, if I assign a new value to A, I'm just changing the address. That's all I'm doing. I'm not, with this operation, changing the data inside the heap I'm pointing to. This stays the same. This is untouched. I'm only changing the value in this table, so the address is a different one. The address A points to. Pointer again. So it's like I'm changing this thing, so it's no longer referencing this memory address. It is now maybe referencing this one. So that is what I'm doing with this line. So if I add a ref in here, I can change the address for A and B up here. But by not using ref, I'm just copying the value straight up as it is. So I'm creating the pointer again here. So overwriting A with a new num down here changes only this address. But the original A up here is still pointing to the initial num 10 true. So ref can still have a meaning, but it's rarer. The important part is, because we have the address, when we reference A down here, we reference the same data, the same values as the A up here. Despite both being separate entries in their own tables, having actual values. It's a sort of indirection. You're not having the data directly, you're having the address which tells you where the data is. Like you're giving your street address to two different people. Both will be able to come to your house and bring stuff to you, or smear graffiti on your wall. But just because you give one of them a different address doesn't mean the other will have a different address. They both have their own address, but they both refer to my address. Does that make sense? Maybe not a good metaphor. Yeah, with that we create classes. And since classes work indirectly, we're only storing a reference to the data. We don't store the data directly anymore like with structs. Classes, custom data types that are defined as a class, are called reference types. Num is now a reference type because it is not data in of itself. If I store a variable of type num, I'm not storing data, I'm storing a reference. A struct we had before is called value type. When I store a variable of type num, and when num is a struct, then I store the data, I store the value. Reference types, you store the reference. Value types, you store the value. When you call methods, you copy the content of the table in here, which for a value type is the actual data you want to store. You copy that over, duplicate it. So you have two versions of that now. With reference types, you copy the reference, the address. So both have their own copy of the address, but they both refer to the same data in memory that they manipulate. And I think I'm gonna leave it at that. There are a couple of things I would like to discuss now, but that's gonna take a bit more than 10 minutes. Next time we're gonna discuss some consequences of this distinction between value types and reference types, and weird effects you might encounter, and things to get used to. It's not difficult, it's just you have to experience it, I guess. Just to get a feeling for how to handle these different types of data. And different types. With it, have a lovely Sunday, and till next time.